Hi, my name is Oktay. Welcome to today's video about the Fullerenes. These are the football molecules. In this picture at the left, you can see the crystals of the molecule C60, which is also called Buckminsterfullerene or buckyballs. And the buckyballs are allotropes of carbon. Allotrope means different form of the same chemical element. For example, allotropes of carbon are diamond, graphite, graphene, graphene, nanotubes, and these fullerenes. At the right, that's the structure of the soccer football. It contains hexagons and pentagons. Buckyballs can be found in nature. The Nanobud contains buckyballs in traces, and the Spitzer Space Telescope found buckyballs in the Milky Way and the Small Magellanic Cloud, which is a satellite galaxy of the Milky Way. This is one example of larger fullerenes. That's the molecule C540. Other examples are C320, C240, and C80. And the Bucky onions. The Bucky onions are smaller fullerenes that are trapped inside a bigger fullerene. For example, C60 fullerene, buckyball, inside the bigger C240. And it could be that these compounds exist in the interstellar medium. This is a picture of Shungite Mineral from Karelia. It contains over 98% carbon and traces of the Fullerene C60 and C70. This is an electron microscope image of Fulleride. Fullerides are solid fullerenes. This is the structure of the Buckminsterfullerene C60. That's the molecule that has the same structure as the soccer ball. It was first produced in 1984 by laser vaporization of carbon in a helium beam. And for this discovery, the Nobel Prize in Chemistry was given in 1996 to Harold Kroto, Robert Curl, and Richard Smalley. This compound was named after Richard Buckminster Fuller. He was an American architect, inventor, and futurist. This is how you can synthesize fullerenes. First step is arc vaporization of graphite in an inert atmosphere or combustion of benzene. That gives you a soot which contains the fullerenes. Second step is isolation of C60 and C70 from the soot by extraction. And the last step is a column chromatography with silica gel, solid phase, and organic solvent. The smaller C60 molecule elutes first with a purple color because it can travel faster. And after a while, you get the C70 molecule, which is in a reddish-brown solution. In this picture, you can see, in this picture, C60 is the red, travels faster, comes out first. And after a while, this can isolate the C70 molecule. This is a method you can use to test the optimum combination of the solid phase and the solvent. This is called thin layer chromatography. You take a special piece of paper which is coated with silica gel or aluminum oxide, and you can test different solvents. You fill the beaker up 1 centimeter with the solvent. It could be chloroform or ethanol or toluene or a mixture. Then you take one small drop from your mixture and drop it here at about 1.5 centimeter distance. Then you put the paper into the beaker, cover the beaker, wait about 7 minutes. The solvent will slowly creep up here. And the different components will be transported at different speeds. And you want something like in this picture, where you have a nice separation. And if you find the right combination of solid phase and solvent that works, this is a thin layer chromatogram, then it will also work in a column chromatography. This is the structure of the C60 molecule, Buckminsterfullerene. It has 12 isolated pentagons and 20 hexagons. Carbon atoms are sp2 hybridized, and this molecule has tension. The most known and stable variants are C60, C70, 76, 80, 82, 84, 86, 90, and 94. And the variants 76, C80, and C84 have chirality, which means they have two different versions. They are mirror images of each other, but not identical. It's like left hand and right hand. The fullerenes are fluorescent in organic solvent. This is a comparison fullerenes versus benzene. Both contain carbons that have sp2 hybridization. There are 3 sp2 atomic orbitals that overlap, make this structure in the middle, this hexagon. And each carbon has one more electron in the p orbital. You put the p orbitals overlap and you get the pi orbitals. And the pi electrons are delocalized. They can move freely in this structure. These sigma electrons are restricted to their orbitals. They are localized, but the pi electrons are delocalized. Benzene is known for its high mesomeric energy. It is aromatic. And this ring is a very stable structure. That's why benzene likes substitution reactions, which maintain this structure. Fullerenes are non-aromatic because they are not flat, and they like addition reactions. And this is an example. This is a typical example in chemistry. With different conditions, you can get different products. So C60 fullerene with oxygen in benzene reacts to this epoxide. And with ozone in the dark, you get this structure. And at room temperature, you get again this epoxide. But with light, you can get the oxygen atom inside the ring, and you get a new ring. This is another example of fullerene, of the reaction of C60 with anthracene in naphthalene solvent. This is called a Diels-Alder reaction. It is a conversion of double bonds to single bonds, and it makes a new ring. At the bottom, you can see the general principle. You have the diene compound that has 2 double bonds, and the dienophile, which has which has 1 double bond, and 2 of this total 3 double bonds are converted into single bonds, and you get a new ring. And the reason why this works is because the carbon-carbon double bond has less than double the bond energy of the carbon-carbon single bond. That's why this reaction is exothermic, and that's why it works. This is the structure of C70 fullerene. It contains 12 pentagons and 25 hexagons. It is soluble in toluene, but not in water. This is the difference between C70 and C60. The C70 molecule contains 5 more hexagons in the middle. Right. This is a picture of fullerene in water. Its applications are in cosmetics as anti-aging cream, in electronics, nanotechnology, medicine. In medicine, it can be used for anti-cancer treatment to make a C60 derivative that can be transported inside the cell. And then you can activate it with light. That converts normal oxygen into reactive oxygen, and the reactive oxygen triggers the self-destruct program of the cancer cell. This is a picture of Fullerides, which are C60 anions. They can be used for energy storage. And some pi-anions are superconductors. The sodium fulleride is not among them because it has a different structure. But the other fullerides, potassium fulleride, rubidium fulleride, and cesium fulleride, are superconductors. However, the cesium fulleride is only a superconductor at high pressures. And at 40 Kelvin, so all these Fullerides are not high temperature superconductors, because the boiling point of nitrogen is 77 Kelvin. And this is a conceptual drawing of a Fullerene solar cell. In this molecule, the C60 is the electron acceptor, and the deuterated conducting polymer is the donor. Unique on top a layer for UV protection, because organic compounds are sensitive to UV light. And one disadvantage is Fullerenes are quite expensive. This is a picture of Endohedral Fullerene. It contains atoms, ions, or clusters in the C60 molecule. One example is lanthanum in C60. It was synthesized in 1985. This add symbol indicates a particle that is trapped inside another molecule. And this compound is a stable atomic trap at room temperature. Its potential applications are in biomedicine and electronics. This is a nice picture of endohedral fullerene, holmium nitride in C80 or scandium nitride in C80 inside a carbon nanotube. This is very impressive. You can see a single molecules. Yeah, that's very, very nice. This is a picture of carbon nanobud. They were discovered in 2006, and these are fullerenes that are bound to nanotubes. And you can make this reaction in water vapor or CO2. And the point of nanobuds is they have a higher chemical activity compared to nanotubes. This is a transmission electron microscopy movie of a nanobud. You can see the nanobud interacts with the molecule that is inside the nanotube. This is a picture of Buckypaper, which are sheets of nanotubes or nanobuds. And you can make a composite material out of this paper, and they have the potential strength of 500 times that of the steel. Buckypapers are interesting as armor material for electronics and for displays. This is a beautiful molecule. It's called Nanocar. It has wheels that are made of fullerenes. Since the single bond can rotate, this means this car has functioning wheels. Right now there's research about nanosensors and nanomotors. And all these technologies combined could lead one day to the invention of nanobots, which could do very useful work, for example, in the human body. This is a nice picture of the world of nanoparticles. And it's a logarithmic scale, x-axis, starting at 0.1 nanometers up to 1 millimeter. At the top, these are the particles in nature, and at the bottom, man-made particles. For example, here, micrometer scale, bacteria cells, here the human hair. Nanometer scale, the viruses, ribosomes. And the small molecules at below 1 nanometer scale. Here are the quantum dots. They are very interesting. They were found in 2004. These are nanoparticles that have a size which is less than 10 nanometers, and they have surface passivation. They are very interesting because of their high fluorescence and high temperature resistance to 800 degrees Celsius. This is a nice picture of my optical microscope of fullerene crystals in benzene. This is a nice picture of contemporary artworks that were created after 1950, which were painted with fluorescent paint. And this is, in my opinion, the best soccer player of all times, Diego Armando Maradona in 1986, when he won the World Championship. He was a really a great player, special player. That was today's video about Fullerenes football molecules. Thank you for watching. Have a nice day. Bye-bye.